against liquefaction triggering procedures. I want to put one more nail in the coffin of the so-called standard penetration test. There's a paper by Jeffries and Davies in 1993 where a site in Canada had several contractors do SPT and several contractors do CPT. After doing this data set, they did statistical analysis. And the best way of estimating the N60 number was to do a CPT and then use a tip resistance blow count correlation. The uncertainty of getting the SPT directly because of the contractor to contractor variation was so large, it was actually statistically better to use a CPT with its uncertainty, which was much smaller, and a correlation, which has uncertainty, to estimate the SPT. If that doesn't tell you about the uncertainty of the SPT, I think nothing does. The hope is we have a simple parameter that can capture the cyclic resistance ratio. We know it's affected by density, fabric, stress history, aging, seismic history, and other issues. So the hope that Professor Seed had was that penetration resistance could estimate cyclic resistance ratio because those things that affect penetration resistance, and as demonstrated in calibration tests, calibration chambers, affect cyclic resistance. So the idea is to calculate a factor of safety against liquefaction triggering. Professor Kramer has mentioned the way to calculate the seismic demand using this equation. This is the peak ground acceleration at the ground surface without liquefaction, most normally from a ground motion model. That gives you your seismic demand. And what we're focusing on is how the different methods use a penetration resistance, in this case, a CPT tip resistance, to estimate this cyclic resistance ratio baseline. I like keeping this clean and then taking my baseline, which is for 7.5 vertical effective stress in 1 atmosphere and level ground, and then adjusting it to what it would be for my particular magnitude of that, my depth or K sigma, my lack of level ground if I have sloping ground. So the factor of safety is the cyclic resistance for the baseline case, modified by magnitude scaling factor K sigma and K alpha, divided by my seismic demand. And Professor Kramer mentioned these factors. Let's start with the Boulanger and Idris 2014. You have the report. It's a modification of the paper or the monograph they wrote in 2008. It was Idris and Boulanger 2008. This is the preferred method in many places around the world. The concept is the cyclic resistance ratio for the baseline case is a function of QC1N clean sand. So it's QC, they actually meant to say QT. It's your corrected tip resistance for a vertical effective stress of 1 atmosphere, normalized, clean sand equivalent. This is the equation that captures the solid line, which is not much different than the dotted line, which represents what they had in 2008. These are cases of liquefaction being manifested at the ground surface. These are cases where liquefaction was not observed at the ground surface. So the threshold is the cyclic resistance ratio. This equivalent clean sand normalized corrected cone tip resistance is a very important parameter. It starts with QC1N, and then you add a fines content correction. So we're really saying CRR is a function of the tip resistance corrected by normalization and fines content. So it's critical that we have a a standardized way of developing this QC1N, and we have a standardized way of adjusting it, because as we add fines, we get too low a penetration resistance for the same relative density, so we have to bump that up to get this clean sand equivalent. If in 1964 we had the Advisory earthquake and the Chichi earthquake where we had a lot of silt liquefaction, they probably would have developed a QC1N silt equivalent, and you would correct your clean sands to silt. Much of the liquefaction in the 64 earthquakes and in 1971 was largely clean sands or slightly silty sands, so we use clean sand as our reference. This important parameter captures the important effects of soil density, the other key factors like fabric and OCR. It's normalized, so it captures the effect of overburden stress, the effects of fines, and it's normalized for the atmospheric pressure. So in terms of QC1N, Boulanger and Idris say at every depth, I take my measured cone tip resistance, they meant to say corrected QT, and you normalize it according to this equation. It looks similar to what we've seen before. It's atmospheric pressure divided by the vertical effective stress raised to the m power. M is a function of density. They know you're using a cone, so they're using the normalized clean sand tip resistance as a proxy for relative density. You need to know the QC1N clean sand to get M to calculate this factor Cn to get the QC1N, which leads to the QC1N to Cn. But so you have to do an iteration. That's not a big deal in spreadsheets because that can be done very rapidly. There is an important thing here is no one wants to use this region of the correction where a small change in the vertical effective stress at very shallow depths could lead to incredibly large changes in Cn and potentially conservative. So they limit the maximum Cn value, no matter what you calculate, to be less than or equal to 1.7. And I would say 90% of all engineers agree with that. And it doesn't matter if you don't agree with it. You have to do it if you do their method. Then there's a change because of the fines content, and that is this equation here. It's shown graphically in black, the change in the tip resistance as a function of fines content. The 2008 relationship is shown in blue, so it's slightly different. One of the important things to pick from this is if I have a clean sand or a slightly silty sand with less than 10% fines, there's a minor adjustment. If I have a fines-dominated matrix, whether it's 40% fines or 60 or 80% fines, there isn't much of an adjustment. The major change is between 10% fines and 40% fines. So for example, at 10% fines, you might have an addition of only 10, where at 40% fines, you can have an addition of 60. Do you want to respond to her? Ignore her.
Give me.
She doesn't want to be ignored. Originally, Idris and Boulanger in 2008 said, you must take samples, you must do a sieve analysis, you must get the fines content. But they were losing out to Robertson and Bride that says, you don't have to do that, you can do everything with a cone. So I think they made a compromise by saying, okay, we'll loosen up a bit, and we'll let you estimate fines content as a function of the soil behavior type index with an adjustment factor. They recognize that was a compromise, so they suggest that if you haven't done fines content measurements on your actual soil to improve this correlation, you should use all three of these lines to estimate CF so that you get different estimates of fines content depending on I sub C, so you can look at the importance of that assumption. If it doesn't matter, don't waste your time. But if it does matter, then you have to probably invest in actually collecting samples and measuring the fines content. I am not a big fan of anyone's correlation between I sub C and fines content. This is a soil behavior type index, very powerful. This is how much of the material passes through the 200 sieve. When I look at changes in I sub C, where it matters, small changes in I sub C can change me from 10% fines to 40% fines. Look at the scatter. Even on sites that are very close together, you see a lot of scatter. So this is a weakness of their method and many methods. So summarizing, they have a calculation procedure for developing in a systematic way QC1N clean sand equivalent. In a general way, it's a proxy for several factors, but most importantly, soil density. The lower the penetration resistance that's been normalized and corrected to a clean sand equivalent, the more contracted the soil is. The more contracted the soil is, the lower the CRR. Then they have the adjustments for, well, it's not a magnitude 7.5. It's not exactly at a vertical effective stress of 1 atmosphere. It's not exactly level ground. They've done some very nice work in this area, and they looked at the shape of these curves, as we discussed earlier, and the shapes are different besides their position. And so if you're going to bring this all back to what is equivalent to a magnitude 7.5, which is about 15 cycles of loading, you're going to end up with these magnitude dependent, but also relative density dependent. As the relative density goes lower, you would expect a flatter curve. As the soil becomes more compressible with silty materials, you'd expect to have a lower curve. So these make sense. They are consistent with the concept of the critical state framework. And again, it doesn't matter. You have to use their magnitude scaling factor if you use their method. In terms of K sigma, I think that's some of the very best work because Professor Boulanger looked at the state parameter and the concepts and said, CN, which adjusts the tip resistance to a normalized tip resistance, that has to be the same kind of model that I use for the K sigma. I shouldn't be adjusting the tip resistance for confining pressure or vertical effective stress and adjusting the CRR separately. So he has integrated those together in a unified way using the state parameter. And so I think this is a very robust K sigma. It's consistent with the state concept. And you see that it actually is 1 at a vertical effective stress of 1 atmosphere. If the soil had a relative density of 0, it would be 1. But as the relative density increases, it drops slower. We often focus on this part of the curve because that may be the foundation of the dam. But recognize critical state soil mechanics says this should continue. I, when I'm allowed to, would continue this. There's nothing that says it should be truncated at 1.1. And I've used values as high as 1.4 in those procedures that will allow me. But if I'm using their procedure, I stop it at 1.1 because that's how they developed their database. You have to be consistent. You can't be correct or right. You have to be consistent with the developers. And so when you use the Idris and Boulanger method, you better get to know Ross Boulanger and Ed Idris because their personality and their experience and their brain, their judgment is enwrapped in it. So you're adopting their personality for a moment in time when you run their method. So get to know them. That's why it's good to go to conferences and listen to Professor Idris, listen to Professor Boulanger. Then K alpha. Actually, Ross Boulanger did some work on this early on. This was a big part of his thesis. It was very fine work. But back in 1997, when he worked with Les Harder on this and updated it, they go, it's too young. You can't get it into the Out at All 2001 paper. I think that was a mistake. I think they just ran out of time. And now it makes sense that you would use this method because it's been backed up by laboratory tests and it's consistent with the state concept. And it's wrong to ignore this for loose soils. Loose soils that are a little bit on the slope are metastable. When they get a cyclic load, they're highly contractive, and you can get a resistance that goes down. If you have intermediate densities, there's not an effect, but I also take advantage of this. It's reasonable, and it's not unconservative to admit that if I have a dense soil with those same kinds of conditions, I'm going to get a K alpha value greater than 1. And so I use these relationships as shown here for K sigma. It's useful to look at the Boulanger, the Idris and Boulanger 2008 EURI monograph, and then look at the report that was written by them in 2014. The major changes, I mean, it had only been 6 years, was to update the CPT database because there were quite a few earthquakes, including those in New Zealand. They came up with a new magnitude scaling factor, which I think is an improvement. They simplified the procedure for fines content, which I understand why they did that in a practical sense, but I don't like it. And then they came up with a new fines content correction, which we can argue about that, but I accept it. And then very importantly, they developed this in a probabilistic framework. When you do things deterministically, you are using the probability of liquefaction of 15%. So when you calculate a factor of safety of 1.0, it's actually biased, a little conservative, because practice says we don't want to be wrong on this, and there is a 15% probability of liquefaction, which means there's an 85% probability that there will not be liquefaction. There are limitations, and they do a very nice job in the 2014 report of showing you the data, the depth of assessment. Most data is for less than 9 meters. Now, some people take that as well. Since we haven't seen liquefaction at greater depths, we don't need to worry about it. No. Remember Lower San Fernando Dam? I showed you a picture in my first talk where there was liquefaction at depth that led to a flow failure that almost killed thousands of people. So liquefaction has happened at depths greater than about 12 meters or so. The limitation is the way we acknowledge liquefaction is typically through sand boils or surface manifestations of liquefaction. I can have liquefaction at greater depths, and I just don't see the manifestations at level ground. You drive a drilled pier through that material, and you go to the Maui earthquake in Chile, and liquefaction at depth caused that pier to punch down 70 centimeters. There are some factors that are depth dependent, and you just have to realize you have uncertainty as you extrapolate where you don't have the data. And that's one of the strengths, I think, of the Boulanger and Idris method, is they have a strong mechanistic underpinning to a lot of their factors. Although, I mean, I can argue, I agree that probably RCD is the weaker of all of their relationships, and maybe they'll change that. Triggering versus manifestation is the thing that we talked about. And then when we get to high fines content, just realize there's very few data on soils that have fines content greater than 40%. So we're not saying that soils that have fines content greater than 40% don't liquefy. We see that they have liquefied. We just have fewer case histories where those soils have manifested ejecta and liquefaction. You put a tall building on a shallow foundation on those sites, you'll see the manifestations of liquefaction. This is the procedure. I just want you to have this so you have this as a flow chart. So if you want to put it into a spreadsheet, you can. Nice thing about the Boulanger and Idris report, as well as their Idris and Boulanger monograph, they have some nice example problem solved so you can check your spreadsheet. I typically find people make mistakes in spreadsheets, so I think it's good to go through it and make the spreadsheet, but you better check it for all these possible cases. And maybe the thing to do is use a program that has been used by hundreds and hundreds of people, where everyone has group thought and found problems with it, and it's been corrected. So I've actually flipped my viewpoint. I thought you should not ever do an analysis unless you wrote the spreadsheet. Now I kind of think you should not take time making spreadsheets that potentially have errors unless you want to invest a lot of time to perfect it. And you should actually use a program like CLIP. I do not get any pesos for selling CLIP. I just found that Peter Robertson, teaming up with a gentleman in Greece who's good at software development, make a very nice program that has a lot of the methods in it, and it's done right. And when people find mistakes, they email them and they correct them. So I didn't have this up, use CLIP. Or make sure you do it right. An alternative method, it's actually been around a little bit longer. It was actually adopted by Young et al. 2001 in the state-of-the-art paper, is Robertson and Ride. It's very similar. You have a corrected tip resistance, you do overburden correction, you make a fines content correction, which they call a ISIP-C correction, to get a QC1N clean sand equivalent. That gives you your cyclic resistance ratio for the baseline case, and then you adjust the baseline case for magnitude scaling factor K sigma K alpha. Robertson has a different personality, whereas Ross Boulanger and Ed Idris are very case history, and they spend a lot of time with case histories. They go through the detail of every case history. They can tell you probably today, you walk up and say, tell me about case history number 32, and they can talk to you about it. And then they have mechanistic underpinning to essentially develop a model, and then they do regression. You do a regression analysis through it. Peter Robertson has more of a concept of what's right. He's very confident of that concept of what's right. He checks it against the data. I've never seen him publish his data set and say, this is why I picked each of my data points. And he just presents that. But he's a very smart person. There's probably very few people in the world that have done more cone work and most site investigations with the cone than him. And it works well, so it's a method that you should also use. You should not do a deterministic analysis with one PGA and one magnitude. You shouldn't just do the liquefaction assessment with one method. As smart as Ross Boulanger and Ed Idris are, they're not perfect. At least one of them will admit that. But Peter Robertson's method offers an estimate by a different method. When they both agree, you should have confidence. When they disagree, you're thankful for knowing that, so that you can work through the issues and say, which one makes more sense? Or maybe I'll bring in a third method to break the tie. So he uses the normalized values that we talked about already. So this is essentially, I think this is almost exactly the same slide as I showed before. It has the same materials. The bottom line is you use an iterative procedure, given your corrected tip resistance and your measured sleeve friction, to turn it into a big QTN, a normalized tip resistance and a normalized friction ratio. One important point, he doesn't actually say you should limit this. He doesn't say you shouldn't. He's silent. But I put a less than or equal to 1.7 here. Then he skips over the whole thing of fines content correction in another way by saying, what I care about is soil behavior type index and how that changes the tip resistance and penetration resistance. So he uses I sub C. Now, two differences. He estimates a correction based on I sub C, which I think is superior, because I think I sub C is superior to fines content. And you don't have to use I sub C to estimate fines content. You can use I sub C directly. So I like that. I don't like the fact that KC is a fourth, or is to I sub C to the fourth power, third power. When you have this variation of KC with I sub C, I'm not as worried. But when you get this rapid change, minor variations in I sub C cause significant changes in KC, that worries me. Especially since, as opposed to everybody else who adds on a fines content correction, he multiplies it. So you can actually go from multiplying the tip resistance by 2 to multiplying it by 3 with minor variations in I sub C. If you look at the work of the late Professor Harry Seed, which is shown in the blue lines for clean sand, 15% fines, and more than 35% fines, if Peter Robertson is correct, he is the only one who's correct, because everybody else has a much tighter fines content correction. He is very aggressive. And I would argue maybe too far to the left. He would say, no, everybody else is too conservative, I'm right. So one of the things I do is I do the analysis his way. I have to do it his way. But then I also put a limit of KC to not use a value greater than 2.5, because I don't like taking a measured value that's been normalized and multiplying it by too large a number. And I see if it matters. And if it doesn't, I go to sleep at night. If it does, I spend some time thinking about it before I have a shot of whiskey and go to sleep tonight. This is the procedure. Again, in case you want to put it into a spreadsheet, I want you to have the step-by-step method of doing this. Okay? There is a minor adjustment. It's what Robertson and Ryan had in 1998, but then he basically found out that N should not just be 0.5 or 0.7 or 1. It should vary as a function of I sub C and effective stress. So that's the improvement that was done in 2009. Now this I always do. I never do his calculation without limiting Cn to be less than or equal to 1.7. I love this because Peter used to be a black and white person. People would do his method and they calculated I sub C of 2.59. It could liquefy. They calculated I sub C of 2.61. Not possible to liquefy. There's no way soil behavior changes magically at I sub C of 2.60. So I would like to think I had some influence in my interactions with him over the last decade to where he's gone to black, white, and gray. And making you think about the fact that if I sub C is less than 2.5, it's most likely a non-plastic, silty sand that can liquefy, and this penetration resistance method has been calibrated for that material. If I sub C is greater than 2.7, it's probably clay-like. You may have a clay failure issue, but it's not a liquefaction issue. And if you're in between, you're in between. Another thing that he has that I hope he's working on, I've asked him to work on it, but he hasn't done this yet. Peter doesn't do what I ask him to do, just like my kids don't. He goes, if I have an I sub C between these two values and a low friction ratio, regardless of what you calculate with this fancy equation up here, set equal to 1. The problem with that is I've been on projects where in the spreadsheet, The soil is just got a ice of C greater than 2.36, and you basically have a Kc value of 2. And then another case, just a little bit further down in the same soil deposit, ice of C is just less than 2.36, and now Kc of C is equal to 1. What he did is essentially put a patch. And the problem with a patch is it's black and white. Minor variations in ice of C cause you to go from Kc equal to 1 to Kc maybe equal to 1.8, 2.0, 2.2. That volatility makes me nervous, and so I look for those cases. It's a nice thing to print out your tip resistance data on this plot and see if you're in this range, completely in the patch range, or you just happen to be right along the border. This is the mathematical expression for the cases when the QC1N clean sand equivalent is greater than 50 or less than 160. Above 160, you say it will not liquefy. For QC1N clean sand equivalent less than 50, this is the equation that he sends you to in another paper, so I rewrote that so you have it in the notes. Now, Peter Robertson is actually all about just doing it for the baseline case. And he's never told me in a paper exactly whose magnitude scaling factor he favors. And he's never gone back and used magnitude scaling factor to change his data set around. So you're kind of free here to do what you think is best. I haven't gotten approval from Peter Robertson on this yet, but I have discussed it with him and he hasn't thrown a brick at me. So I don't think I'm that wrong. I use Idris and Boulanger's magnitude scaling factor to adjust CRR for magnitude scaling factor for Robertson and Ryan. Because there was debate at that time over which one's correct, and in the end, the Youd et al. Paper uses Idris 1999. Idris is like a fine wine. He's better in 2008 than he was in 1999. In fact, every workshop I went to from 1995 to 1999, he was constantly changing his magnitude scaling factor. So it was a work in progress. So I look at if Idris had finished it in 1999, it would have been this. So I look at this as the correct scaling factor to use with Robertson's method. In 1997, when the workshop was held and when the paper was published later, they had a lot of discussion on K sigma. So to be consistent with Robertson and Ryan as presented in Youd et al., I used the K sigma that's a function of relative density and vertical effective stress that's in that paper. And then they're absent on, he doesn't say anything about K alpha, so I go ahead and use the Idris and Boulanger K alpha. The third method that's prominent worldwide is the Moss, Seed, and others method. They were actually the first to do a robust statistical analysis using Bayesian updating. They actually brought in Professor Derek Karigian, who was at Berkeley at the time, to help them with that. They do have this improvement that Professor Kramer talked about in terms of R sub D. R sub D should be a function of the intensity, frequency content, and the response characteristics of the system. So having it be a function of the intensity of the ground motion, the VS 15 meters, and the magnitude is consistent with all of the site response analysis I've ever done. So for most sites, I think this better represents R sub D for a magnitude 7, and this is a simplification of that. But I use R sub D by Chet et al. In the Moss method. Of course I use the R sub D that Idris and Boulanger used in their method. A strength of the Moss method is Ray Seed is part of all of these. He's one of the academic leader of pulling this all together. And so he made sure that the CPT data gave consistent results with the SPT and the shear wave velocity. one of the things that consultants have a problem with is when they do SPT and CPT at the same site, and they use someone's method, and one says it's going to liquefy, and the other method says it's not going to liquefy. That's another reason just to do CPT. Is why do something that you have less faith in that might actually put you in a situation where you have to explain away why it's not giving you the right answer. I just want you to have the methodology written out. I'm sorry, I just wrote it out by hand. I haven't written it out in fancy typeset yet. But at least you have the steps 1, 2, 3 so that you can put it in a spreadsheet if you want. Or you can just use CLIC because it's been implemented in CLIC and it's been checked. And when I first got the spreadsheet from Rob Moss, when I was checking my spreadsheet, we disagreed. We both had errors in it. Now I have a spreadsheet from Rob Moss that's correct, and I use his spreadsheet as a check, but I basically get the same answer with CLIC, so I use CLIC. And these are the equations. Again, one of the values is you don't just calculate a cyclic resistance ratio, you can calculate a probability of liquefaction triggering. Okay, so by several methods, given the CPT data, you've calculated a factor of safety against liquefaction triggering. It's good to step back and say, well, what does that mean? I like to look at this plot of residual excess pore pressure after strong shaking as a function of the factor of safety against liquefaction triggering. This tells me if my factor of safety is 1.5, 2, 2.5, nothing much matters. If I have a lot of uncertainty and I don't know if the factor of safety is 1.5 or 2.5, this is telling me I don't care. If I calculate a factor of safety of 0.6 or 0.7, I don't care as much either because I know I have a problem. I have to mitigate it. It's when I'm in this range where I'm thinking I should sharpen the pencil. So my rule of thumb is if I calculate with these methods consistently a factor of safety against liquefaction triggering less than 0.9, I think it's going to liquefy and I should spend the money on mitigating. If someone takes a site that has a simplified factor of safety of liquefaction triggering of 0.6 and does some fancy three-dimensional viscoelastoplastic analysis and calculates the triggering factor of safety is 1.1, I take all of those words and I throw them in the garbage can and I trust the simplified method. The simplified method is not that bad. And analysis can be really bad. And so I trust the empirical method over that. Now, if I calculate a factor of safety against liquefaction triggering of around 1, and I do a well-calibrated model like PM4 SAN, and I do that analysis correctly, or I do a couple of different analyses, and I calculate the factor of safety is not actually 1.05, but it's 1.15, then I trust the analysis. So typically, if the factor of safety is greater than 1.2, it's probably acceptable. It always depends on contingencies. One thing is, as Professor Kramer mentioned, in the US, they've pushed the geotechnical engineers to doing liquefaction evaluation at the MCE level, the 24 75-year return period level. Almost everything liquefies at that level. Given the conservatism of that hazard calculation, and given that I know with the factor of safety is equal to 1, the probability of liquefaction is 15%, in those cases when I'm working on a project in the US, I will accept a factor of safety of 1.00001 as being acceptable. If liquefaction is triggered, we have to evaluate the consequences. And it's the effects that matter. So Professor Kramer will talk about residual strength and what effect that can have to flow slides. He'll also talk about reduced effective stresses and how that can change the dynamic response of the system. And it looks a lot like a soft play site sometimes, but it's actually pore pressure generation and softening because of that. He's already talked about how dilation can lead to acceleration spikes. If you're a structural engineer and you have to have the site liquefy to base isolate your building you're not a structural engineer. You may not liquefy. And if it does liquefy, you may get dilation spikes. I've heard people talk about the positive effects of liquefaction. There is no positive effect of liquefaction. Except I guess it gives me consulting money. Then you have sedimentation and ejecta that causes significant deformation. You have shear strains that lead to deformation. And even if you don't get liquefaction, or if you do get liquefaction, you still have built up excess pore pressures. They are going to dissipate over time. You're going to get reconsolidation. You're going to get settlement.